Okay, let me explain K-word or K-tuple. And say you are comparing two sequences. And here that first sequence is the same in both case. This one and this one is same. And against this, take it as a query sequence, your query sequence. And you have two different sequences in your database, and this is one, and a slightly different sequence is compared against the second pairwise comparison. So the sequences which is shown in the bottom will have slight difference. For example, here we have TC, here it is AG, and instead of this T, here we have A, and like that. There are slight differences in the string that is presented at the bottom. Okay, now you perform the comparison and you can see that there are mismatches, matches, both present in both the strings. Okay, and both sequences were having 5 matches out of 10. So which will be a better one? You can say that both were having same matches, same number of matches and mismatches. But one, as we discussed in the previous session, when we consider the edit distance is actually only 2 for the first, and there are it requires 5 edits, 5 different editing or mutation events is occurring on the second sequence. So we can say that this is actually a better preserved sequence, and here we have some 5 pairs of sequences that is continuously available 5-letter sequence which is conserved here, and here it is not like that. So the possible number of mutations in the second string is higher. Okay, so this is a result of the comparison, and in the case of the edit distance of the first sequence, it is only 2. Okay, now we can consider that first sequence and consider a 5-letter keyword, for example. If you are considering the k-meres or the word length to be 5, then this region constitutes a 5-letter keyword. Finding longer words is statistically less. If you can look into a DNA and find a continuous string of match, like instead of 5, if you are looking for a continuous match of 6 or 7, finding such a longer segments of similarity with your query sequence and the database sequence is minimal. If you are looking for a letter by letter, single letter comparison, there will be millions of possibilities are there. But if you are looking for 2-letter words, then also you will have a sufficient number of hits will be there. But with the increase in the number of letters in the word, a possibility of exact match in the database will be minimal. So as you asked rightly now, if you are looking for a keyword exact match of 500 or 1000, then it is nearly impossible, because there will be at least a few mutations in the database sequence, and if there is a slight variation in that keyword, then it will be rejected, because if you are considering a keyword, exact match should be there, and no spelling mistakes or changes will be accepted in between. Okay, so if you are looking for an exact match, just like a find button, find function in a Microsoft Word, in which you can type the query word or any word, and if there is a spelling mistake, it will not find an exact match in the word. Like that, in a very large set of data, you can search with a query word of a length 2, 3, or 4, any word. With the increase in the number of letters, and if there is any mistake or if there is any error, you can't find the exact match. So that's the concept. So the number of words should be minimal. That is generated. Keyword, the length of the keyword should be minimal. It should not be that much higher, because there are possibilities that a single mutation in that region will result in rejection of the entire query. So 5,000 or 500 or 1,000, that is not a good option for you. And also one of the point is that the in the case of all genome sequencing, our entire length that needs to be compared is 500 to 1,000. So you are comparing two sequences of length 500. In the previous example, both the sequences were having total length of n. So exactly if the sequence, one sequence, your final target is to see whether they are matching or not. So for which purpose you will break that 500 base pair length into different length words, multiple words, and see whether there are any local matches for each and every word. That is the actual keyword based comparison. Your total length of the sequence that you are comparing is only 500 in the previous example. So there is no point in constructing a keyword of 500. So our problem is to simplify that, and there is a random match or finding in a database of a 500 length word is nearly impossible. So in that case, you will look for a keyword of 3 or 4 or 5 like that. So it will be randomly matched at some other points in the database sequences. So that is the optimal length that is recommended. So you see the example of this query string which is shown here. How you generate a keyword. For example, keyword, the length of the keyword k can be assigned as 8. So if you are generating word of length 8 from this query sequence, then the k tuples can be, set of k tuples can be generated. For example, 8 letters starting from the first is t is this one, and starting from the G, the second letter G, you can take 8 words and 8 letters, and the second word is generated. Likewise, you can generate different keywords or 8-letter query strings in this fashion. So it is like the first 8 will be taken as a first word, then starting from the second, the next 8 words will be taken as the second word, and starting from 3, next 8 will be taken as the third. And likewise, you can generate a set of 8 letters as a k tuples or keywords if your query length is 8. And how many possibilities are there? How many words can be generated? It is n minus k plus 1. So that is the formula that can be applied to calculate the total number of words that can be generated, where n is the number of bases. If you are taking a 500 base pair read of a DNA or a sequencing instrument, Sanger sequencing instrument, where the generated fragment that you are comparing is of a 500 base pair length, then in that case, n is a 500 and k is 8 because we are generating words of length 8. So n minus k, that is 500 minus 8, 498 plus 1, 490 to 93. 493 possible k words can be generated. So that is the total number of words that can be generated from a query string. So likewise, you can generate words. And if at least one word of I and j, where generally when you are expressing such strings, query strings, I and j were considered in mathematical terms as x and y axis represented the string I and string j, which will be represented in the comparison matrix on x and y axes. So if the string I, at least one word of the string, the first string, that is I, is not found in the second string that you are comparing. So your comparison is between two sequences of say 500 base pair length. So I will be 500 and j will be 500, the second string. And if at least one word of this first string is not found in the second one, then you know that it is completely different. So that likewise, you can look for words from I and whether it is matching with the words of a j. So that is the actual comparison. Instead of letter by letter comparison, the 8-letter keywords or k tuples will be generated from both the strings I and j, and both I and j represent here the two strings under comparison, two DNA sequences of 500 base pair length. And if at least one word is not matching from between both the strings, then that means they are entirely different. I need to consider the statistical significance also. I and j might share words by chance only. There's a possibility that only random matches may be expected. For example, if your keyword length is less, then there is a possibility of finding such a random matches. But with the increasing length of the k to an optimal level, you can have a better match of the sequence. Here, the length of the word the word list is from every string. For example, from the first string I you can generate a word list, and here one example is there. A string of I is the first string is shown here, and the keyword length is set as 2, means you are generating 2-letter words. So these are the possible words or that can be generated, or keywords that can be generated, and each will be represented and a list of the words with their number of occurrence. For example, GC is occurring at 2 positions, that is at one at the first and second position, whereas the other letters, other words will be represented only once. So you can generate a list of the words or an index of the words of the string 1 or string I can be generated. And likewise, list of words of a J can also be generated. Okay. So you have some mathematical formulas for calculating the overall time that is required for computation of these things, and it is not relevant now. Anyway, we have two strings I and J, and you generate a list of words of I and list of words of J, and now match whether it is matching. So we have two common words of if you compare this AT of the first string, then you have two words, common words. Then CA, again you have two common words, and this is not having any match. And likewise, you compare both the sequences, or the word by word comparison will be done, and see whether there is any matches or mismatches between the two strings. If the same word is present, then that match can be addressed. So the first point is generating of the list of words, then comparing the list of words between the two strings. Then exact matches can be found using binary searches. Example, where T, C, G, T occurs in I. For example, binary search is done by, in this case, the k-tuple length is 4 letters. So you can just like you are searching for a Word document with a query term in the find box. You can you perform a binary search with one word from list I and see whether it is present in J or not. And for large K or large number of for longer K words, large K means the length of the word will be higher. The table size is too large to compute the common word count in the previous fashion. So that means if you are looking for a K of 200 or 300, then it will be too difficult to compute. So usually that type of large, extremely large K values is not good. Instead, an approach based on merge and sort can be utilized. I will show you how it is merge and sort, because an optimal length word like 4 or 5 letters or 8 letter K word that can be generated, and you can generate the word list. Then you can finally merge these words to generate the final alignment instead of going for a very large keyword. The common keyword technique can be combined with the local alignment algorithm to yield a rapid alignment approach. Here you can see that the keywords from one string is generated, and here the length of the K is 3 letter words were generated from this string. So break query into words. So that is your query. For example, you are trying to search NCBI database with a new sequence in your hand, 500 base pair sequence of a 16S rRNA of your isolate, and if you are giving that one, it will be broken into different fragments of say 3-letter words, and a list of the words will be generated. Now break the database sequence similarly into words. So the database is having multiple sequences, maybe 226 million sequences are there. So that can also be generated because it is already there. Broken words or the list of the words were already present in the database. So each sequence can be generated with such a words. Instead of searching your sequence one by one, for example, letter by letter, as we discussed earlier, the word by word matching, your first word will be matched against different words, word list of this sequence, second sequence, and third sequence, and every 226 million sequence in the database can be compared. If you are performing a wide search, every sequence or the list of sequences or list of words generated from every sequence in the database will be compared with your query sequence. So you will have a list of words of your query and a list of words of your database. So now your query word will be matched against words in the first sequence in the NCBI, second sequence in the NCBI, third sequence in the NCBI. Everything will be matched against this one, and compare the word list by hashing and allow near matches. Wherever such a matching is found, that will be located. And then you can see if it is a match, then that sequence can be aligned with these particular matching positions. So your database sequence, or your query sequence and the database sequence will be aligned word by word. Wherever matching word is found, that region will be initially aligned. And in the subsequent steps, this region, and if your sequence is having a very good similarity, or if it is the same, then you can see the words will be matching and completely it will be constructed. If it is having a similarity only and not the exact match, you will have some regions where words were not matching. If your sequences were both the sequences were same, then by positioning the keywords of your query with the keyword list of the concerned database sequence, it will be exactly matched and at all points. So you will have a continuously constructed list of keywords positioned at each and every point. So your sequence will be completely aligned, but by word by word matching and aligning them together. And if in the case of similar sequences where if exact words were not matching, such aligned regions will be extended by additional algorithms, which we will discuss later. And this region will be further analyzed to construct the total alignment. And that type of methods will be discussed in the subsequent sections. So this is about the keyword and keyword based sequence matching. Is it clear? Yes, sure. No, actually, that part is done by the computational algorithm. For example, if you are comparing it to the NCBI database, the word length and other things will be is a part of their algorithm. You don't have to say separately set it. Okay, because the word length, because based on their the actual limiting factor is the size of their database, the NCBI database. So you are just giving a query of say a 500 or 700 base pair length query. So their algorithm to make that search or the similarity or comparisons to speed up that comparison, what they are doing is that your fragment will be broken into fragments or into list of words instead of just looking for the entire 500 word length query as such in the database. It will be broken as say 5-letter or 6-letter or 7-letter words, and the same thing will be done in their database sequence also, because it is not the you can mute the mic, right? Okay. Actually, what they are doing is their database or the word list of NCBI is already there. If they are, for example, they are adopting a 7-letter word list, it is already there, just like a Google index. Google actually they keep the list of the words, or the index of the words is already there for Google for comparison. If you are typing a query word, they are not generating the word list in real time. They have an index of the words of the database, and if your query is then submitted, your query will be divided into the concerned query length, their desired query length or the keyword length, and it will be compared against the concerned database or the index of the words that is present there. So you don't have to to bother about the length of the query word, and that will be modified accordingly or updated accordingly in the NCBI or the database that is preparing that index.